Hey everybody, Trey here. Welcome back to another video. Now that we're moving out of our traditional severe weather season into the summer, it's time to start looking back at some of the more notable cases from this past spring, and boy is that a long list. Tornado activity ramped up significantly in late April and continued in earnest through the bulk of spring, leading to one of the most active years for tornadoes on record up to this point. This included a number of interesting and unique events, many of which are on my list of case studies to cover over the coming weeks. The first one of these is the prolific April 26th outbreak that most notably ravaged parts of eastern Nebraska into western Iowa. Notable tornadoes included the EF3 that went through portions of Lincoln and Waverly, Nebraska, the high-end EF3 that produced major damage in Elkhorn, Nebraska, another EF3 that overturned planes at Elba airfield on the outskirts of Omaha, and the beastly multi-vortex wedge tornado that produced high-end EF3 damage in Miden and Harlan, Iowa. As you can see, many of these tornadoes were intense but still extremely photogenic, making this a very fruitful outbreak for storm chasers. This ended up being the most active tornado day of the entire season, with nearly 150 tornado reports from Nebraska down to Texas, the bulk of which came from the Nebraska-Iowa corridor. In this video, we're going to break down the meteorology behind the April 26th outbreak to determine why this setup was such a prolific tornado producer. So without further ado, let's go ahead and get started. The April 26th outbreak was very well forecast, with the first explicit indications of potential severe weather from the SPC coming in the Day 7 outlook issued on April 20th. After several tweaks to the outlined area, the SPC upgraded to a level 3 out of 5 enhanced risk with the initial Day 2 outlook on April 25th, centered on the Nebraska, Iowa, Missouri, Kansas confluence area, and it would remain that way with the morning outlook on April 26th. The enhanced risk coincided with a 10% hatched area for tornadoes, potentially some strong, as well as a 30% hatched area for large to very large hail. By afternoon, the enhanced risk area was extended southward into southeast Kansas, eastern Oklahoma, and northeast Texas, given increasing confidence in tornadoes, potentially some strong, and large to very large hail across these areas. Alright, let's dive into the meteorology behind the April 26th outbreak. As always, we'll start out with the 500 millibar map at 12Z, 7 a.m. Central Daylight Time on April 26th, and right away you can see the culprit. We see a broad, long wave trough situated across the western half of the country with a couple of well-defined short waves moving through the flow. One developing back in here over the west coast. This one will be important in the next day's outbreak across the southern plains, case study on the April 27th event coming soon, and this one moving through the central plains with its associated 60 to 70 knot jet streak. Notice the textbook negatively tilted nature of this trough, which, as we've discussed on the channel ad nauseum before, is often more favorable for robust severe weather because it tends to lead to a more intense low-level response, i.e. a deeper low-level cyclone and stronger low-level jet. The trough moves slowly off to the northeast throughout the day, and if we were to break up the jet streak into our typical four-quadrant model, that puts eastern Nebraska and western Iowa squarely in the left exit region, which is the favored quadrant for ascent and in turn severe weather by mid-afternoon. Forcing was somewhat more limited farther south from southeast Kansas into northeast Texas, given a slightly more glancing blow from the trough, but enhanced flow aloft and favorable dynamics within the right entrance region of the jet streak seemed to provide enough large-scale forcing to support isolated convective development with southern extent. Up at 300 millibars, a broad area of defluence began to overspread the central and southern plains during the morning of the 26th. By 18Z, notice how the flow aloft across central Nebraska was basically due southerly, shifting to slightly more southwesterly over Iowa. This defluence was present across the southern plains as well, leading to widespread background ascent that would prime the atmosphere for storm development. At the surface, a well-developed low had taken shape the previous day and had meandered to the Kansas-Nebraska border by the morning of the 26th. It slowly moved off to the northeast and deepened slightly throughout the day, attaining a position in southern Nebraska by midday and near the Nebraska-Iowa border by 0Z. To start the day, widespread 60s dew points had made their way up to the Kansas-Nebraska border and were feeding into the low, which was situated near the Norton, Kansas area. A warm front was draped to the east and southeast across northern Kansas, and a well-defined dry line extended southward from the low. Note the shift in winds from more westerly across western Kansas into the Oklahoma and Texas panhandles to southerly across the low plains to the east, as well as an increase in dew points from the 30s and 40s west of the boundary to generally 60s to the east. The warm front would lift northward and the dry line eastward throughout the day, coincident with the northeastward advance of the surface low, maintaining a narrow tongue of robust moisture representative of the warm sector, feeding right up into the low. 72 over 65 at Grand Island, 76 over 64 at Hebron. Coupled with the left exit region dynamics at play, this would deem the surface low a favorable area for storm initiation. Normally, this moisture tongue might be too narrow to support a long-duration severe threat, but it was lifting northward with time, as shown in morning model data, so any storm that developed within the moisture axis would remain in it as it trekked off to the north or northeast. Even though this may not have been a true cold core event given only modestly cool temperatures at the center of the mid-level trough, the surface low target had a lot of similarities to cold core events. We've discussed this diagram from Geyer and Davies 2004 many times before on the channel, link in the description box below. But as a refresher, it shows the most favorable configurations of ingredients for cold core tornado events. Looking at panel B on the right, we can see that the 500 millibar closed low and surface low must be in close proximity to one another, and that the favored area for tornadoes is immediately ahead of the surface low and intersection point of the dry line and warm front. This is exactly what we saw with the April 26th event. The 500 millibar low began to close off as the day progressed, displaced only slightly to the west of the surface low. The area of interest existed within the narrow tongue of moisture streaming up into the low, just ahead of the intersection point between the dry line and the warm front. The area ahead of the dry line would continue to warm and moisten throughout the morning and early afternoon as well, priming the environment for the quote-unquote main show, a round of storms separate from the surface low activity that would move into the enhanced risk area with time. Given a more southerly component to the mid and upper level winds, deep layer shear vectors were southwesterly to even south-southwesterly across central Nebraska, which created a near optimal degree of perpendicularity between them and the initiating boundary, the dry line. Therefore, a more discrete storm mode was favored. Taking a quick peek at 850 millibars, we see a broad, generally southerly low-level jet of 40 to 50 knots extending from the Great Lakes all the way to the Gulf Coast ahead of the large and deepening low-level cyclone. This helped to continue to pump low-level moisture northward into the risk area and increase low-level shear, particularly across Nebraska and Iowa, where surface winds were more backed. Let's take a look at the 12Z observed sounding analysis at Omaha. We'll do a more in-depth model proximity sounding analysis in just a bit. We started off the day north of the warm front, hence the fairly cool surface temperature and stout low-level inversion, but we did have quite a bit of elevated instability already in place at 7 a.m., over 1100 joules per kilogram of most unstable CAPE. This was expected to improve as the day progressed with the approach of the shortwave, surface heating, and the advection of the warm sector into the region. We'll come back to this in a bit, as thermodynamics played a big role in this event. In addition, take a look at the wind profile. A combo of significantly backed surface winds and the 40 to 50 knot southerly low-level jet was leading to impressive curvature in the low levels of the hodograph with nearly 600 meters squared per second squared, 0 to 1 kilometer storm relative helicity. This was also forecast to persist into the afternoon given the gradual deepening of the low-level cyclone and continuation of backed winds in the warm sector, particularly in eastern Nebraska and western Iowa. Therefore, assuming adequate destabilization, the parameter space was likely to support supercells with a strong tornado risk. One of the question marks going into April 26 was the degree of morning clouds and convection, but those uncertainties were quickly squashed as the morning progressed. Taking a look at visible satellite, ample clearing rapidly moved in from the south and southwest, with cumulus and even initial convective attempts already apparent in the warm sector ahead of the surface low by 10 to 11 a.m. The first storm of the day developed near Kearney, Nebraska, immediately ahead of the surface low by 11 a.m. As this storm became robust, additional cumulus developed farther southeast along the dry line and rapidly developed into supercells by 1 p.m. So we've established that the environment appeared to be supportive of widespread, possibly significant severe weather. Now let's dive into some of the individual storms within the outbreak, as well as their proximity environments, to see why this became no ordinary significant tornado outbreak. We'll start with the first supercell of the day that developed immediately ahead of the surface low. This storm evolved out of a couple of blips near Kearney that eventually coalesced into a single supercell. After an initial split, the right split became dominant and began producing tornadoes near Ravenna. Notice the velocity couplet that develops near town. Here's a shot of the first tornado this storm produced as it was roping out. The original tornado then occluded, notice the northward motion of the hook, and a new tornado developed near Rockville. An interesting evolution then takes place as a new updraft develops south of Farwell, just east of the ongoing supercell, and almost immediately begins rotating despite anemic reflectivities on radar. This should give you a bit of a hint at the low-level thermodynamic environment, especially with so much ambient vorticity from the nearby warm front and surface low. We'll come back to this in just a second. As it approaches Farwell, you can see a low precipitation hook echo extending out from this new updraft, coincident with the velocity couplet. Reflectivity then increases drastically with this new storm and the old storm dies, indicating that the new storm has become dominant. Velocities also ramp up significantly during this time, and the storm produces the first of 3 significant long-lived tornadoes beginning near Farwell. The first tornado was in progress for over 20 minutes and was quite large, as you can see here, producing EF3 damage to a farmstead near the town of Elba. The supercell went on to produce two more significant tornadoes, a largely rain-wrapped, half-mile-wide EF2 near Wolbach, and a 66-minute-long EF2 from Wolbach to the area northwest of Albion. Let's now take a look at the progression of the environment in proximity to this storm. We'll be analyzing a series of RAP model soundings taken at Grand Island, Nebraska, about 27 miles southeast of Elba. We'll start out at 12Z, 7 a.m. Central Daylight Time, and we see lots of similarities to the 12Z Omaha observed sounding we discussed earlier. Above a fairly stout low-level inversion, there was a bit of elevated instability, and we had a pretty potent wind profile with strong deep layer and low-level shear to start the day. As we head into the midday time frame, just before the supercell began producing tornadoes, the wind profile remains potent with effective storm relative helicity in excess of 200 meters squared per second squared and impressive curvature in the low levels of the hodograph. In addition, we had nearly purely streamwise vorticity in the low levels. As a refresher, that's when the storm relative wind vector, drawn from the storm motion to the level of interest on the hodograph, and the horizontal vorticity vector, which is always perpendicular and to the left of the hodograph, are parallel to each other. And we can see that's the case through the lowest few kilometers of the atmosphere. So our wind profile was certainly supportive of tornadoes. But let's face it, we see this kind of profile fairly often throughout the season with sometimes limited results in the tornado department. What took this to the next level, in my opinion, were the thermodynamics. We went from this at 12Z to this at 17Z. Look at how fat that thermodynamic profile is. Over 2,300 joules per kilogram mixed layer CAPE, and with observed temperatures in the low 70s near the tornadic supercell, slightly higher than the RAP's estimate of 66, we can assume that mixed layer CAPE was actually a bit higher than that, perhaps approaching 3,000 joules per kilogram. In addition, lapse rates were very impressive throughout the entire profile, with surface to 3 kilometer lapse rates in excess of 7 degrees Celsius per kilometer, and mid-level lapse rates between 8 and 9 degrees Celsius per kilometer. This ensured extremely robust updrafts. Low-level instability was also off the charts, with nearly 200 joules per kilogram of 0 to 3 kilometer CAPE. We've talked ad nauseum about the importance of low-level instability in aiding in tornado genesis. When low-level instability is strong, updrafts can more efficiently tilt and stretch surface vorticity or spin into the vertical, which makes tornado genesis much easier. And with ample vorticity near the surface low and warm front, the Elba supercell was easily able to attain rotation through vorticity stretching and become an efficient tornado producer. Not to mention the already optimal tornado-favorable background wind profile. Couple that with the upper echelon thermodynamics we just discussed and a discrete storm mode, and you get an environment favorable for significant tornadoes with any supercell that can persist within it. Now let's take a look at the environment in proximity to the tornadic supercell that tracked through portions of Lincoln and Omaha. This supercell came out of the convection that developed on the dry line just before 1 p.m. This convection started out fairly messy, with several updrafts in close proximity to one another before cleaning themselves up into two dominant supercells. The northernmost storm struggled while the southernmost one intensified. Notice the continual merging of nascent updrafts into its forward flank, including this small supercell. This likely played a role in initiating significant tornado genesis, as the storm produced its first tornado on the northeast side of Lincoln immediately after this merger occurred. This tornado would produce EF3 damage between Lincoln and Waverly during its 12-minute long path. The storm then cycled as it moved into the suburbs of Omaha, this time perhaps being nudged by these much weaker storms on its southern flank. This nudging process has been shown to induce significant tornado genesis in some new research that will be coming out soon. More on that in a later video, and that seems to be exactly what happened here. As those two auxiliary storms move closer, the hook notably wraps up and a strong tornado vortex signature appears in the velocity data. This represented the next and most intense tornado this storm would produce, a high-end EF3 that remained in progress for nearly an hour, most notably devastating a portion of the town of Elkhorn. Notice the well-defined debris ball at the tip of the hook. The tornado dissipated northeast of Blair, just on the Iowa side of the Missouri River. The storm wrapped up a couple more times before things got messy and the supercell fizzled out. To analyze the proximity environment, let's take a look at a series of RAP model soundings at Omaha beginning at 12Z. We see a similar progression to what we saw with the Grand Island soundings. We start off with a stout, low-level inversion well north of the warm front, but with extremely impressive wind profiles. Throughout the day, we see gradual destabilization as temperatures warm and the warm sector makes its way into the region, and by 21, and especially 22Z, we see a fairly textbook profile for significant tornadoes. Upwards of 1,700 joules per kilogram mixed layer CAPE with nearly 140 joules per kilogram 3 CAPE. Steep lapse rates of 7 to 8 degrees Celsius per kilometer make up the entire profile as well, with no remaining inversions or layers of weaker lapse rates. These robust, nearly perfect thermodynamics were coupled with a very impressive wind profile, even more impressive than that in proximity to the initial Elba supercell. Strong veering and strengthening of the low-level winds with height led to incredible hodograph curvature with ample streamwise vorticity and over 400 meters squared per second squared effective storm relative helicity. It doesn't get much more favorable than this for strong to violent tornadoes. Oftentimes, we'll see these kinds of impressive wind profiles paired with thermodynamic environments that aren't nearly as robust. For example, here's a rap sounding at Norman, Oklahoma from the following day, April 27th. Sneak peek at the case study on that day coming soon. And we have an incredible wind profile, but a thermodynamic profile with some issues, such as the warm nose and drier air around 700 millibars, saturated mid and upper levels, etc. This seems to be fairly common with these upper echelon wind profiles, and you still might get a good number of tornadoes, but storms might not be as efficient in producing them. In the case of April 26th, we had a pristine thermodynamic environment with none of these issues. Beautiful temperature dew point spreads, steep lapse rates throughout the entire profile, no remaining inversions, fat cape. When you pair an upper echelon thermodynamic environment with an upper echelon kinematic environment, nasty things are likely to happen. In addition, the tornadoes spawned by the Lincoln supercell were quite visible and photogenic, and that can be attributed in part to the wind profile. Notice the subtle backing of the winds in the mid-levels, going from south-southwesterly about a kilometer or two off the surface to more southerly above 3 kilometers. This likely helped vent precipitation off to the north, well away from the mesocyclone region of the storm, making the tornadoes easy to spot. Additional storms developed to the south of the Lincoln Elkhorn supercell and quickly became severe. Notice how many updraft mergers happen before a dominant supercell takes shape. This often needs to occur in environments of strong deep layer shear so that individual updrafts avoid being shredded by that intense shear. Once the dominant supercell emerges near Louisville, we see continued mergers into the forward flank of the supercell leading up to significant tornadogenesis on the northeast side of Omaha near Epley Airfield. Additional mergers were occurring to the south, developing into another tornadic supercell that ramped up as it crossed into Iowa. It produced an initial weak tornado near Pacific Junction before producing its first significant tornado, an EF3, near Trainer. Once these mergers were complete, intense tornadogenesis once again occurred, this time near Neola. This would become the large, long-track EF3 that devastated parts of Miden and Harlan, Iowa. Eventually, storm mode became much less favorable for tornadoes. Taking a quick look at the proximity soundings leading up to the Harlan-Miden tornado, we can see a progression similar to that of the soundings back west. Moderate instability both in the deep layer and in the low levels develops by late afternoon, paired with an absolutely wicked low-level wind profile, perhaps the most favorable we've seen yet within this event. Half-moon-shaped hodographs packing nearly 450 meters squared per second squared effective storm relative helicity, plus impressive streamwise vorticity in the low levels paved the way for very efficient tornadogenesis, especially with such strong 3-cape and constructive storm interactions at play as well. Storms continued to fire off the dry line to the south through late afternoon and tracked into northwest Missouri and southwest Iowa by evening. These supercells spawned numerous tornadoes, including several EF2s that did damage in places like Creston, Osceola, and even the Des Moines metro before storm mode degraded. As shown in this series of rap soundings at Creston, Iowa, the environment, even slightly farther removed from the surface low, was still ripe for tornadoes, some strong, with adequate instability and impressive wind profiles. Nebraska and Iowa weren't the only places to get in on the action. If you recall, the significant tornado threat extended well south down the dry line, and isolated supercells ended up firing in southeast Kansas. Forcing was a bit more neutral down here, as this area was almost right at the core of the jet streak instead of purely in the left exit region, like areas to the north, so storm coverage was much more spotty along the dry line. Eventually, a single dominant supercell took shape and produced multiple tornadoes across eastern Kansas and western Missouri, including this tornado near Fredonia, Kansas, just before 4 p.m. A quick glance at the RAP proximity sounding at Chanute, Kansas at 21Z, 4 p.m. Central Daylight Time shows a very favorable environment for tornadoes with slightly higher dew points than areas farther north, over 2,000 joules per kilogram mixed layer CAPE, nearly 150 joules per kilogram 3 CAPE, and ample hodograph curvature leading to nearly 250 meters squared per second squared effective storm relative helicity. All of this, combined with a very discrete storm mode and favorable storm interactions and mergers throughout its life cycle, yielded the long-duration tornado threat with this supercell. And finally, a somewhat forgotten part of this outbreak were the supercells that occurred in the Waco, Texas vicinity around midday. These spawned some of the first tornadoes of the outbreak and were somewhat unexpected, at least regarding timing, as storms were forecast to hold off until mid to late afternoon in this region. Subtle forcing on the southern fringe of the main trough, perhaps weak surface convergence, as well as an already weak cap continuing to weaken through the morning, led to tornadic supercell development in this area. The RAP proximity soundings did a poor job of handling the environment down here, so we'll take a look at the 12Z observed sounding at Dallas-Fort Worth. Notice only minimal convective inhibition remained at this point, with further erosion of this little warm nose through midday. The profile was characterized by extremely deep low-level moisture, with the moist layer extending all the way up to nearly 700 millibars, providing plenty of fuel to sustain surface-based storm development. This moist layer resided beneath some drier air and steeper lapse rates aloft, which helped build almost 2,000 joules per kilogram mixed layer CAPE. Strong low-level shear was already in place at 7 a.m. with large looping hodographs and over 400 meters squared per second squared effective storm relative helicity, thanks to a 50-knot southwesterly low-level jet. While perhaps not as pristine as the Nebraska-Iowa portion of the outbreak, this environment certainly favored tornadoes once supercell development became a guarantee. So that's going to do it for this video. Hopefully you got some insight into why the April 26th outbreak was so prolific. Really, it wasn't one thing in particular that was rare or unique, like, say, a Gerald or a Moore 2013. Rather, it was the confluence of upper echelon ingredients that came together to spawn such an event. The stage was set as a textbook negatively tilted trough made its way into the plains, acting upon rich low-level moisture across a broad region from Nebraska and Iowa southward to Texas. Thermodynamics were about as pristine as it gets, with moderate to strong deep layer and low-level instability and very steep lapse rates throughout the entire atmosphere. And when you couple that with ample surface vorticity, intense shear, and nearly purely streamwise vorticity in the low levels, supercells can very efficiently produce tornadoes. Not to mention the discrete supercell mode and favorable storm mergers and interactions that took place. April 26 was the great example of how upper echelon ingredients must come together perfectly in order to get an upper echelon outbreak, and looking back at the meteorology of the event, it's no wonder this setup produced the most prolific outbreak of the year. Thanks for watching, and we'll see you in the next video.